Hello guys, so in this example we're going to go over a concept called directional derivatives, and in this problem we're prompted to find directional derivative of a multivariable function along a vector. So what's our function? Our function is f of xy is equal to cosine of x divided by y. What's the vector? Well, the vector is plus 3 in the x minus 4 in the y. And this is the formula we use. The directional derivative is equal to partial x dotted with our unit vector. So the first thing we do in step 1 is we're going to find the partial x and partial y. So our function f of xy is equal to cosine of xy. So now with respect to x, so this derivative is going to take a lot of work. So I'm going to do this with respect to x and with respect to y. And I'm going to draw a line separating the two of them. So we're going to have to apply the chain rule. So what is the chain rule? The derivative of the outside times the derivative of the inside. Or we can set this up the proper way using f, g, f prime, g prime. So our f is cosine of u. Our g is the inside function, which is u, which is x over y. Our f prime, the derivative of cosine would be negative sine times u. And then the derivative of g prime would be, with respect to x, the derivative of g prime, the constant is 1 over y. So that one remains, but the x goes to 1. So furthermore, we apply the chain rule, and we know that the chain rule is the derivative of the inside when we're given a function within a function, which is the case for here, cosine of x over y. We know that its derivative is equal to f prime times g prime. So in knowing that, we know that our partial x is equal to f prime negative sine u times g prime, which is 1 over y. Furthermore, we know that partial x is equal to negative 1 over y times the sine of u. What's our u? Our u is x over y. So that is our partial with respect to x. So now with respect to y, we again apply the chain rule. So we set up our f and our g. We know f is cosine u. Our g is the inside function, which is u, which is x over y. Our f prime, we take the derivative of cosine u, which is the same as last time, so it would be negative sine u. And our g prime with respect to y, not with respect to x. The x is treated as a constant, so the x will remain, but we're taking the derivative of 1 over y. So applying the power rule, that's y to the negative 1. So y to the negative 1, the derivative of that is 1 over y squared. So now we're going to apply the chain rule. So basically, we know that the chain rule is f prime times g prime. The derivative of an outside function times an inside function is equal to f prime times g prime. And we know f prime times g prime is equal to negative sine u times our g prime, which was minus x divided by y squared. We simplify this a step further. We know f prime times g prime is equal to our partial y. And we know that our partial y is negative sine u times x over y, the inside function, times negative x over y squared. And again, if that derivative is a little complicated, 1 over y, treat it as y to the negative 1 power, and then you just apply the power rule, and you'll get negative 1 over y squared. And in doing this, we know the negative signs cancel out, so our partial y is equal to x over y squared times sine of x over y. So now that we have that, we have partial x and partial y. So now that we have our partial x and partial y, which was honestly a lot more difficult to compute than most problems, but now that we have partial x and partial y, the next step for step 2 is we're going to go ahead and find a vector for these partial derivatives. So all we're simply going to do is we know that our vector will be partial x, partial y. So partial x, we're simply just going to put in our partial x, which we got to be negative 1 over y times sine of x over y. So that goes where partial x is. And for partial y, we got x over y squared times sine of xy. So that's it for step 2. We just found the vector for these partial derivatives. Now for step 3, keep in mind that in the original problem we were given a vector, right? What vector were we given? We were given this vector of plus 3 in the x, minus 4 in the y, and then 0 in the z. So we don't worry about z for this particular directional derivative. But now that we have that, now what we're going to do is we're going to find the unit vector of this vector. So our vector was positive 3 minus 4, and we know the formula for a unit vector. If you don't know how to find unit vectors, I have a video on that. But anyways, this is the formula. It's the vector divided by its magnitude. So for the magnitude of vector, we have plus 3 squared plus negative 4 squared. So we know 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, the square root of 25 is just 5. So our unit vector comes out to the vector divided by its magnitude. So we know positive 3 divided by negative 4 over 5. And when we distribute the 1/5, we get plus 3 over 5 minus 4 over 5. That's our unit vector. So that's step 3. So for step 4, what we simply do is we're going to plug this formula to find the directional derivative. So what formula are we going to use? Well, we're using this one right here. So the formula for a directional derivative would be the partial derivative vector dotted with the unit vector. And you will use this a lot. If you're doing mechanical engineering, you will deal a lot with unit vectors, partial derivative vectors, or any engineering field in general. But now we use this formula. The derivative, the vector of the partial derivatives dotted with the unit vector. So we know it's fx partial y dotted with the x component of the unit vector dotted with the y component of the unit vector. This is the formula that we use right here. So now we know from step 2 that our vector for partial derivatives is this one right here, negative 1 over y times sine of xy for x, and then for y it's x divided by y squared times sine of xy. So that's our that's our formula to get directional derivatives. So now this is our partial x, partial y. We're going to dot this with unit x, unit y. So what is our unit x component of unit vector? Plus 3 over 5. Y component of unit vector is minus 4 over 5. I'm color coding red for y and then teal for x, y. So that way you know which ones get multiplied by each other, because I've seen people that mess up on this step right here. So now what we're going to do is we're going to apply the dot product. So plus 3 over 5 dotted with its x component, with its x counterpart, would be negative 1 over y times sine of xy plus negative 4 over 5 dotted with its y component would be x over y squared times sine of x over y. Then when we simplify this, we get plus 3 over x plus negative 4x So furthermore, we simplify this and we factor out a 1 over y. We factor out a sine x over y. And then we're left with minus 3/5 minus 4x over y. And one thing I did notice was that in the previous step, I made a mistake right here. That plus 3 is supposed to be a minus because when it multiplies by negative 1 over y, but I corrected it right here. So keep that in mind as well. So that's our final answer. So 1 over y times sine of xy, we factor that out and we're left with, because that's common for both terms, and then we're left with minus 3/5 minus 4x over y. And then, so in quick retrospect, what did we do? Well, let's do this real fast. So in step 1, all we simply did was find the partial derivatives of x and partial y. And this one took a lot of work because we had to apply the chain rule for both terms. And well, we did that. So this is just a lesson from Cal 1. Again, as I said earlier, if you don't know how to apply the chain rule, I have a video on that. So feel free to watch it on my Cal 1 playlist. So we did that. For step 2, we simply just got our partial x and partial y, put it in vector form. In step 3, we identified our vector, found its unit vector. And in step 4, we dotted them together. We plugged them into the formula for directional derivatives. We apply the dot product because that's essentially what we're doing, is we're dotting them. And we came out to our directional derivative is 1 over y times sine of xy times negative 3/5 over 4x times y. And I noticed that I also forgot to factor out a 1/5, but no worries. I'm going to add it here real quick. So this right here is supposed to be a 5 on the denominator. So that's our final answer. Hello guys, so in this video, in this example, we're going to go over how to find directional derivatives given a point, not a vector. And well, keep in mind that for directional derivatives, we need a vector. So, which I'll get to later on. But what do we do if we're given a point, not a vector? Well, anyways, we're given this function of x squared times y cubed minus 4 times x times z. And then we're given the formula of directional derivative, which is the partial derivative vector times the unit vector. And we're given a point. So for step 1, we're asked to find partial derivatives of x, y, and z. So doing so, partial derivative with respect to x is 2x times y cubed minus 4z. Partial derivative with respect to y is 3x squared times y squared. Y, we don't worry about the last term, the minus 4xz, because there's no y's, so all that's treated as constant. Partial derivative with respect to z, we don't worry about the first term because it's a constant, because there's no z terms in it, but the second term has a z. So the partial derivative of negative 4xz with respect to z, we drop the z and we're left with minus 4x. So in step 2, we are asked to identify the vector for f using partial derivatives of the partial derivative vector will be f of x, f of y, f of z. So this will be our partial derivative vector. Furthermore, I color coded them so that way you can see which one's which. So our partial x will be what we computed for partial x, 2x times y cubed minus 4z. Then our partial y will be 3x squared times y squared. And our partial z will be minus 4x. So that's our, so now we have a vector for a partial derivative at least. But to get a directional derivative, we need two vectors. So we need a vector, we need another vector. What vector is this directional derivative acting along? Well, let's see. So in step 3, we need to identify vector for a directional derivative. So here's the key step. So one thing we do need to keep in mind is we need to note that even though we are only given a point in 3D space, unless otherwise specified, assume the initial point is at the origin. So in this case, we have an initial point of x naught, y naught, z naught at 0, 0, 0 at the origin. Why? Because now we have a vector, because we have a point in space. What's our point in space? Our point in space was given to us as p of -1 in the x, +2 in the y, 0 in the z. And we have an origin at 0, 0, 0. So now we have point A to point B in 3D space. That's called a vector. So now the original point is 0, 0, 0. I color coded them again. And then our second point, P1, is -2 +2, 0. Basically what we're given. So unless otherwise specified, you must assume that the initial point is at the origin. So now our vector is the final point minus the initial point. So P1 sub x minus P0 sub x will give us our x component of our vector. P1 sub y minus P0 sub y will give us our y component of our vector. P1 sub z minus P0 sub z will give us our z point of our vector. So in doing so, all we simply do now is we just apply subtraction. -1 minus 0 for the x, +2 minus 0 for the y, 0 minus 0 for the z. And in doing so, our vector comes out to be -1 in the x, +2 in the y, and then 0 in the z. So now that we have a vector, we can move on to step 4. So now that we've identified the vector from our directional derivative, the next step would be to find the unit vector. So to find the unit vector, all we're simply going to do is just take the unit vector, is we're going to apply this formula right here. So we know that the unit vector is the vector divided by its magnitude. So we're going to use this because later on we're going to dot this with our other vector that we have for partial derivatives. So the unit vector, the first thing we have to do is we have to find the magnitude of our vector. So the magnitude of our vector is equal to the square root of the x term, which is -1 squared, plus +2 squared, plus 0. So now that we have that squared, we solve this even further. We know that 1 squared is 1, 2 squared is 4, and we know that 0 squared is 0. So simplifying this, we get our magnitude to be the square root of 5. So we know our unit vector is our vector divided by its magnitude. And we know that our vector is -1 in the x, +2 in the y, 0 in the z, divided by its magnitude, which is -5, which is the square root of 5. So now what we're going to go ahead and do is we're going to distribute the square root of 5 divided by each term. So furthermore, we get -1 over the square root of 5 for x. For y, we get +2 over the square root of 5. And for the z, we get 0, because 0 divided by the square root of 5 is just 0. So that's, now we have our unit vector. Now we can move on to step 5. So for step 5, what we're going to do is we're going to plug into the formula to find directional derivatives. So what formula are we going to use? Well, remember at the beginning of the function, anytime we're trying to find the directional derivative of a multivariable function along a vector, we use this formula right here. So we know the directional derivative will be the partial f dotted with our unit vector. So what's our partial derivative vector? Well, it's this one we got right here in step 2. This one that we took the partial derivatives and then we put them all into a vector of fx, of partial x, partial y, partial z. So now that we have that and we know our unit vector is equal to those numbers, now what we're going to do is we're going to go ahead and plug them into the formula to find directional derivatives. So again, we know the formula is this right here, and we know this is simply partial x, partial y, partial z dotted with unit vector with respect to x, unit vector with respect to y, unit vector with respect to z. So now that we have these values, what we're going to do is we're going to apply the dot product. So our partial x, what was our partial x? Partial x was these terms right here. So I'm going to go ahead and use them. So 2x times y cubed minus 4z. Partial y is 3x squared times y squared. Partial z is minus 4x. And then we're going to dot this with the unit vector. It's negative 1 over the square root of 5, positive 2 over the square root of 5, and then 0. So now when we simplify this further, we're going to join all these terms together. So partial x is dotted with the unit vector, the x of component of the unit vector. So I'm going to put brackets around that. Plus partial y is dotted with the unit vector, the y component of the unit vector. And then we know that partial z would be 0 times negative 4x. Furthermore, we simplify this. We distribute the negative 1/2 to both terms, the negative 1 over the square root of 5 to both terms, and we get those values. And then we distribute the plus 2 divided by the square root of 5 to both terms. We get these values because 2 times 3 is 6. And then 0 times negative 4x, as we know, is going to 0 out. So furthermore, we simplify this. Keep in mind, dot product gives you a scalar, but in this case, it's a directional derivative, so it gives you a directional derivative. So we simplify this a step further. 4z over 6x, y squared over the square root of 5. And now our directional derivative, one last step, is we can factor out the square root of 1 over the square root of 5. We can radicalize this and write it as 5 over the square root of 5 over 5 divided by 5. And we simplify it by just leaving the terms on the numerator. And our directional derivative comes out to this. So that's how we do directional derivatives. So what did we do in a nutshell? Well, in a nutshell, we did quite a bit. The first thing we did was our function was x squared times y cubed minus 4xz at the point of negative 1, positive 2, and 0. The first thing we did was we found partial derivatives. In the second step, we put these partial derivatives in and we made a vector for them. In step 3, which is a key step because we were given a point, not a vector. So unless otherwise specified, the initial point is always going to be at the origin. So it'll be 0, 0, 0 in a three-dimensional space. So in doing that, to find the vector, we subtracted the final point minus the initial point, p1 of x minus p0 of x, etc. It was just subtracted by 0, but you still have to show that step because it's a point. And directional derivatives act along vectors, not single points. So keep in mind that you always have an initial point of 0, 0, 0 unless otherwise specified, and the line between that origin to the point is called a vector. In step 4, we found our vector and we computed a unit vector. And in step 5, all we simply did was do the arithmetic to find the directional derivative applying the dot product. So thank you for watching.